Okay, so we're just reviewing kind of what we know about logarithms. We know they're the inverse of exponentials. We know we can graph the exponential, and then we can swap the x and y to get the inverse. So sometimes that can be easier than doing the brute force change of base formula. And the change of base really just lets you calculate the decimal approximations for when you're doing your XY table, whereas you could also graph the inverse and then do transformation. So if you had this log base 6 of x minus 2, for instance, then I could transform it. So first of all, it's a base 6. So because of that base 6, I could graph like 6 to the x, and I could plot all those points specifically. Notice it has an asymptote here at y equals 0. And so now that asymptote is going to flip along the xy. And so let's say we have now like this log. It's now going to become that with this asymptote. And then now, so there's really two key points on a graph, asymptote, and then the point that is a 1 that came from here because power of 0 is 1. And log of 1 is 0, therefore. And then finally, the transformation. So if you have a transformation of minus 2 in x, that's going to move it to the right by 2. So then basically, this 1 point will be at 3, that 0 line will be at 2, and it's just going to move over like that. So you could basically use the inverse and then the transformations, or you could do decimal approximations for graphing the logarithm. And graphing actually helps us with a lot of things. You can use a graphing tool as well. So you could do sort of like a graphing calculator. And what graphing helps us do is, first of all, it shows us all the possible answers, but also when you're solving equations with logarithms, it's a nice way to check your answer. For instance, I have an example here. It's partially done for us already. Like sometimes if you had something like this, like you're looking for when y is 70. So let's say you're trying to solve this whatever equation, and this one's not a logarithm, it's an exponential, but you can do this for a logarithm as well. Graph the left side, graph the right side, and you get 2, right? So the 70, y equals 70 is going to be one equation, and y equals this is going to be another equation, and you're looking for when the intersection is. So sometimes if it's too complicated of an equation to solve, it can help to graph and look for an intersection, especially with some of the equations that become very hard to solve. So that's why the graphing part is important. Another part of why the graphing part is important is to just get a sense of what you're doing with the numbers, because if you don't see kind of the general trend or what to expect, then it's easier to make mistakes because you're not sure of what to expect. So you just take whatever you've gotten as an answer without questioning it. Okay, so that's some things we know about logarithms. So let's just recap a little bit. We'll backtrack and see if we can remember some of these things. So remember, expanding and combining. You're using these properties that we listed last day, and so there was the product rule, there was the quotient rule. So if you have a log of, say, m times n, you're going to do what? So multiplication inside becomes what outside? You can type that in the chat. And then, right, if you have a division inside, that becomes what? And if you have exponent, what does that do, right? These are all different properties that we developed. And then we also need change of base. So for multiplication, anyone remember, what does this become? Well, it'll be log m and log n, and how are they connected? Addition, yeah, nice. And that's because the exponents added when we were multiplying the bases together. And so for division, it's going to be subtraction. And the next one was just a multiple of those. p just drops out because there's p of these log m's now. So here are some different kinds of questions you may expect. Combine into a single logarithm, expand. Another thing would be graph. And then another thing would be solve. These are the basic sort of kinds of problems that you can expect. And then there's also the problems that have to do with applying this into a context. If you have some sort of A equals B, I'm allowed to do one of two things other than what I've already been allowed to do. So I'm allowed to add to both sides, I'm allowed to subtract to both sides, I'm allowed to multiply both sides, I'm allowed to divide both sides, right? I'm allowed to square both sides, but again, remember that this is always both sides. The only time you have a distribution, so if I had like B plus C, like I would still do it to the whole side. I wouldn't do it to each thing. So I can, if I think of it that way, I can square both sides, I can root both sides, and now I can take both sides as a logarithm of the same base. So that's my new thing. I'm allowed to do that to both sides. And I'm also allowed, if I have this, it's just B plus C is whatever, I don't know, whatever it is, I'm allowed to take both sides as an exponent. Again, whole sides, not pieces of sides. The reason why I emphasize this is because we are so used to going like 2x equals 3 plus 4x. If, if I wanted to multiply everything by 3, I could go, we're so used to going times 3 times 3 times 3, but that only works for multiplication division because multiplication division are distributive. But technically what we're doing there is we are multiplying both sides. Not that I would need to multiply by 3 here, but we are multiplying both sides. And then because multiplication is distributive, it goes in, but we've always just kind of like done that sometimes like without thinking through that part. But that only works for multiplication and division. I'll show you an example of where like it's easy to make that mistake. But you might be kind of reminded of when you had, say, root x plus 2 equals x plus 5. We were not allowed to square each term. We were only allowed to square both sides. And the same thing applies here. You can log both sides and you can take both sides as a base of the same thing. This is what we are allowed to do because those things don't change our truth statement. We can try that out with examples. But that being said, if I want to deal with something like this, I can basically reverse the process. If I want to get at that x, what's in my way before, like if I had 3x equals 9, it's like, what's in the way of my x? Well, I had to divide both sides by 3. We're doing the same thing now, but we're thinking, what's the opposite of taking an exponential with base 3? The opposite is taking a log base 3 of both sides, because that's going to kind of cancel out my base 3 and neutralize that exponent. That exponent's kind of come down. Log base 3 of 3 is 1 because it is the inverse of itself. And so I'm left with just x minus 2 there equals log base 3 of 81. So now that the x has come down, if the exponent had the variable, now it's come down, I can now deal with it as a algebraic form. Okay, and so we might want to think about what this is. Maybe we can simplify it. 81, I can think 81 is actually a power of 3, isn't it? So this one is 3 to the power 4. We've seen that before. If you could not simplify that, You might consider it as a change of base formula and find out more specifically from a calculator what that is. Like you can always do that, but then it's a decimal. So if they want exact values, you just leave it as is. But in this case, we do actually have this here. The 4 can come down. Log base 3 of 3 is 1, right? So it's asking 3 to the power of what is 3 to the power of 4? That's a 4. And so then I can deduce what x is, adding 2 to both sides. 6. We always want to try it back because sometimes you have things going wonky as well. Okay, so that's an example where the x is as an exponent. So it's an exponential equation. And so I can take the log of both sides with the same base. Sometimes I want to isolate this so it's by itself, so it's nice and clean for me to do that. And the other option is if you have a logarithm, then you would take both sides as a power of the base of that logarithm. So if this is a base 10 logarithm, I would take both sides as a power of 10 in order to sort of like neutralize that log. So when I neutralize it, 10 to the power of log 10, because those are inverses, it's just going to be 9x plus 1. And that's going to give me 10 to the power of 3, which is 1,000. And I mean, I could have taken this and rewritten as its exponential, which is actually 10 to the power of 3 equals 9x plus 1. So in this case, because it's not super complicated, I could see it both ways. And then, you know, you would minus a 1, so 1,000 minus 1, and then divide by 9. Yeah, so maybe, you know, try it back in and see if it works, that sort of thing. Now, if your bases are not the same, if I took log base 3 of both sides, it's going to cancel this one, but it's not going to cancel this one. It happens the same the other way. And I still have an x in the exponent there, and it's trapped. I could pull it out, and then it would be x plus 2 times log base 3 of 5. I can use a distribution because this is technically a number. The way I would continue this is I would get my x's together so I can factor out the x. I would pull out the x. I'm keeping these as exact values because I want you to see how that would look. And then I would divide both sides by. But yeah, when you have different bases, it's going to be way more complicated. But sometimes it's possible, as we can see here, divided by. Yeah, so essentially I started off by taking log base 3 of both sides. I could have started off by taking log base 5 of both sides. That neutralized one of mine so that I could kind of get it on, then I could get the x's on one side. But yeah, this is definitely a little bit ugly. Sometimes once you're not sure about solving something, you can always graph both sides. So you could graph this as one equation, graph this, and look for intersects. So where the intersection points are will give you kind of an approximate answer. Most of the time you'll see examples more like this. So this is the last one that I'll show you. You want to put that together first before you apply anything. So that's super important. So then I would use my log laws, use it as a multiplication. And then now I could just do, okay, 10 to the power of 2 is that. And then you're gonna now have quadratic. And then you'll get everything to one side. You've done this sort of thing before. Factor or quadratic formula. And then always check, because sometimes there's a domain issue. So it's just like with roots, you want to double check your final answers because sometimes there are domain issues because the logarithms have to be positive inside. Just like when we considered solving questions that had a root or irrational, let's say, these all had things that had to do with the domain. that potentially would create a no solution, even if you did find a solution through the mechanisms that we learned. So when we squared both sides, you know, like maybe your answer does give you something correct, but you always have to check it. And same with this, right? If we multiply by the denominator, and that's because the domain here, x cannot be -2 for a rational. And that comes from, if you think of the graph of it, it can't be at -2, or just it can't divide by 0. And then like for a root, that x plus 2 had to be greater than or equal to 0 because the graph was like this. So that means that x had to be greater than or equal to -2 because when I subtract 2 from both sides. So as long as x is greater than or equal to -2, in my answer after solving, I'm good. Like, so these are just things to check, like check the domain. And then check your answer if it fits basically the question, because something might have gone wrong with the domain as you were solving. Like if you squared it out, you might have not noticed it. And then later on, that answer actually doesn't work. So the same thing happens to exponentials because they have a restriction, or logarithms, because they also have a restriction on the domain, right? So if you have something like log of x plus 2 equals 5, just as continuing our examples, logarithms generally have this sort of thing. So the domain of a regular logarithm is always x is greater than 0, not greater than or equal to, but greater than 0. It's always positive inside the logarithm. And that comes from its inverse, which had all real numbers, but the answers were always positive for an exponential. You couldn't get a negative answer. And so basically, that'll mean that x plus 2 must be greater than 0. Therefore, x has to be greater than -2. So the domain of this function is that x has to be greater than -2. So when I solve it, once I apply all the solving techniques, my answers should be in that range. If they're not, then it means that when I plug it in, there's a problem with the domain. It'll give me an error. So I don't know, let's see if we can put it on the calculator. So that should be a plus. So it'll actually move the other way. So it's actually there's an asymptote here. It's just this graphing calculator is not really showing it very well. So basically what that means is if I had put in -10, it wouldn't have an answer. Basically what I mean is if you get an answer and when you plug it into the log and it gives you an undefined, you're going to have a problem and you're going to have to reject that answer. So just be careful. It doesn't happen very often, but always check your domain. Okay, so now solving these. So for the first question, we have a log on both sides. And remember, we can simply, as long as it's the same base on both sides, if it's different bases, then it's not great. But these are both base 10. I can apply the inverse of the log, which is the exponential, to both sides. And that actually eliminates my log because it gives me just what's left inside. And so then that's just a regular equation that I've seen before. It's a quadratic that I need to factor. I don't know, does this factor nicely? I think so. So x is either -1 or 7. Now, I needed this inside to be definitely positive. So I can double check that those both satisfy that. So just make sure you go back and check because it's possible that if it makes it negative, then there's a problem. The second one, you need to do something first before you do anything. We can't just take everything as a power of 2. Like we can't just go 2, 2, 2. So a very common error here is to go like this. You're like, oh, I could just do it to everything. You cannot sprinkle that inverse over an addition. It is not distributive. That only happens with multiplication over addition. So what that means is always combine your logs as much as possible, right? So if you combine these, that'll be log base 2 of, it's a plus. So that means we're going to multiply, right? So if we multiply the inside, that'll be x times x minus 4 in here. Now I can actually do something to both sides, and to both sides I'm going to apply the inverse of what I want to get rid of. I want to get rid of this log base 2. The inverse is taking it as a power of 2, so I have to take this side as a power of 2 as well. Okay. So then you're left with just that inside and the 2 to the power of 2, right? So that also is the common error, to miss that and to just make it equal 2 and to forget to take it to the power. Okay, so again, we've got a quadratic. I don't think, because of that negative, I don't think we can actually factor that. Base squared minus 4ac. I think it'd be pretty easy to complete the square here, actually. You'd have this, you'd move this over. Then you'd think half of this. Yeah, we could also use the quadratic formula. Yeah, so half of this is 2 and squared is 4, but then I minus the 4. This part becomes x minus 2 squared. And then I get minus 4, which is minus 8. And then I move the 8 over, square root both sides. So that's going to give me x minus 2 is plus or minus. And if I pull out that perfect square of a 4, that'll be 2 root 2. And then if I add the 2, I have 2 plus or minus 2 root 2. So yeah, you should also get that from the quadratic formula. Yeah. So again, you'd want to make sure that if you estimate what that is on your calculator with the decimal values, that when you plug it in here, you're not getting negatives into or zeros into those logs. And so one of these might actually be rejected, because if I go 2 minus 2 root 2, that's going 2 minus more than 2. So that's going to be a negative. I think the negative will have to be dropped because it won't satisfy the domain. So these are one kind of equation where you have a logarithm in it. I would say that it's kind of similar to when you have a square root type of equation. You're trying to get it kind of like so that the root is by itself. So it's kind of like there's one root and you're squaring both sides, which is the inverse function of a root is squaring it. Whereas here, again, you're combining the log and then you're taking the inverse function of a log, which is a power of, right? So the other option is perhaps it starts as a power type relation, and then you need logarithms to help apply so that we can actually access that x value. Because right now, for instance, this one, power is a power of 2. And so to sort of counteract taking 2 to the power of something, the inverse of that is taking the log base 2 of it. So one way would be just to try to make this as a power of 2 and see if you can just equate the powers. If you can't, then applying a log base 2 on both sides can do the trick as well if you just want to plot away with sort of a strategy. Doing log base 2 of 2, and then this comes up front, keep it in a bracket. I'll still write this so you see, but this actually cancels out as 1 because 2 to the power of what is 2? So this is a 1, so that's gone, which is exactly what we expected because taking the inverse of that should just result in that. And then now we have log base 2 of 1024. So we actually have 3x plus 2 is log base 2 of 1024. And so now we need to use a calculator potentially if that's what you want to do, or you could, I think this is probably a power of 2, but I would have to check as well. So to evaluate this, there's two ways. One, you could do log of 1024 as log 10 over log base 10 of 2 as the change of base formula. Or you could try to identify if 1024 is a power of 2, and that will be the exponent. Log 1024. See how, okay, watch this. I think you can see it. Divide by, if I do that, a lot of people make this mistake. And then now that second log is actually in the bracket. I don't want it to be in the bracket. I want to close the bracket and then divide by the log of 2. So what does that mean? I think we have a 10. So 10 means that 2 to the power of 10 is 1024. Let's check that. 2 to the power of 10 is 1024. So we've just found a way to inverse that. Okay, so this equals 10. So therefore, 3x plus 2 is 10, and we can subtract 2 from both sides, and we get 8/3 as our answer. And then we want to just double check and make sure that works. Because it's an exponential, we don't have that problem with a domain. Yeah, we can still check that it works, but remember the graph of an exponential has all real numbers as its domain, so we can put in any number and we'll always get an answer. So what about this next one? What would we do to both sides? I'll give you a minute to think about this. There's 2 here. See if you can apply the strategy we just did on these ones, and just maybe start with question 14 and think, what do I apply to both sides? And then how do I get x by itself? And then try not to round anything. Like, you don't want to really round anything. Like, if this did not simplify, I would have left it as log base 2 of 1024, because then it's an exact value. Yeah, so what kind of logarithm do we need on both sides? What base? We need a base of the base of this one, right? So since it's base 6, we would want log base 6 of both sides. And that's because that way it will release that operation there and make that just an x, because the x will drop down. Log base 6 of 6 is going to be 1. And then you're going to get log base 6 of 50, which is log 50 over log 6. And because that is a, that's going to be an approximation, they would leave it like this, or they might leave it as ln 50 over ln 6 if they took ln of both sides. I think for some reason the book had this answer, but you know, this is correct as well because it is the same thing. So yeah, typically you want to answer in either a standard log or a ln. So if there is a different base, you can do the change of base there. Okay. So for this next one, what do we want to do on both sides? Base 3? Yeah, so let's try that. Log base 3 of 3 to the x plus 1 and log base 3 of 251. So this will go away and you have x plus 1 is basically log 251 over log 3. You may have gotten that differently. You may have taken a log of both sides. Just want to show you both ways. If you just took any kind of log, it does. In this case, I could have not used that base. Maybe I just took a regular log. Then this x plus 1 would still drop down. You'd have log 3 here, and you'd have log 251 here. And then x plus 1 equals the log 251 over log 3. So again, you could have done this one both ways as well. So I just want to show you that you could have taken a log of both sides, you could have taken a ln of both sides, you could have taken a log base 3 of both sides. I just want to emphasize that as long as you're doing the same base on both sides, it's going to all work out. And sometimes you'll have to like expand this, potentially depending on the equation. In this case, we don't need to, but we will have to minus that 1 away. So essentially what we'll have is log 251 over log 3 minus 1. And so some people may want to rewrite that with a common denominator. So if this is log 3 over log 3, I think the answer key for this one actually has log 251 minus log 3 over log 3. That's an alternative way. This or this, those should be both right. I think in Alex, they would probably give you some guidance on how they want their answer, or they'll just accept either of them. Perhaps it already has a built-in calculator. If you have troubles, just let me know. They could have also had ln 251 minus ln 3 over ln 3. Like these are all the same because I could have taken ln on both sides, which is base e. It's another popular one. I actually like using ln because it's just one less letter to write, but that's just kind of a lame reason. Okay, and just another one here. This one has two different bases. So this one, I could take a base 3 of both sides, I could take a base 4 of both sides, or I could just ln both sides. So I'm going to just go ahead and do it as if I did a ln of both sides, just because I just said that I like ln. But you could have used log, you could have used a different base as well. So let's say I did that. So this is going to come down as the power law states. Now, ln 3 is just some number and ln 4 is just some number. It's like pi or e or, you know, root 2 or something. So now I'm going to, because I want my x's to come together, this is the most complicated case I think you would get. You'd have that distribution going on. So I'd have x times ln 3 minus 2 times ln 3 equals 2x times ln 4 plus 1 times ln 4. Whenever I have something like this where the x's are in different places, in general, we bring the x's together. So x ln 3 minus 2x ln 4. I could have written that slightly differently, but that's fine. And then I bring this one over ln 4 plus 2 ln 3. And then the reason why we brought these together is typically if this was 4x minus 3x, I would just go 4 minus 3, right? You're collecting the like terms. An aspect of collecting like terms is really factoring it out. So because I don't want to simplify that, I'm just going to keep it as is. And so now when I divide by this amount here, it's going to go away, and that's what my x is going to be. So this is the exact value expression of the solution. And obviously you want to potentially like see what that is on your calculator. If you do that, make sure you put bracket over bracket so it contains all of it as you type it in. But you can get an approximate value, but in general, we prefer exact values when possible so that someone else can decide on the accuracy of that. So this is a good example to refer to if you have, most likely if you have two different bases and then more things happening in the exponents, that's going to end up happening where you have to kind of collect the like terms. Okay, so that is the meat of Module 5. There's a few other sort of contextual things to be aware of places where logs are applied. Here's an example, like carbon dating is basically specifically looking at how much carbon-14 is present. And generally we have a model for that, which is exponential. And so sometimes if you want to find that t for the certain amount that you get, then you're going to need a logarithm to solve it. What's similar about these situations, and most of them have to do with this idea of exponential growth or decay. So there's a general sort of format for exponential growth or decay. I'm going to rewrite this bigger here. This one I find is quite important. This is, again, natural growth and decay because it's E. If you remember, we had compound interest was like that, but then when we did continuously compounded interest, had this idea, the PERT, right? It's the principal times the E value, which is that base rate that is it's growing by, to the R times T. Notice how that is so similar to that general formula of an initial value to the resulting value, which is like your RT. K is the K factor. It's a constant. It's the growth rate constant. In economics specifically, that's your rate. But they're using K as the K value in general for any sort of situation that you would be applying this to. And T is obviously your unit of time. So just to compare that with our continuous compound finance type formula, that was PERT. These are basically like acting in the same way, just so you see that relationship there. And that is a growth. The growth is happening based on what K is, or based on what the rate is. Obviously, you might be seeing decay. Maybe you're losing 2% per year. So it's actually going to start decaying. And so that is signified here by these K values. So if the K is positive, it's going to be growing. And if the K is negative, it's going to be falling, right? And time is always greater than 0 because that's time is a constant. So basically, decay is if your K or your rate is less than 0, and it's growing if it's greater than 0, right? Hopefully that makes sense. Your initial is just your starting amount that you're multiplying everything by, because that's where you're starting at time 0. So this structure of exponential growth and decay can be really helpful in sort of identifying different things, like whether you need to know the rate, whether you need to know the initial value. Things like half-life of a substance or doubling rate of a substance can be easily applied as well. So if you had a principle that you're starting with, maybe your question is just, how long is it going to take my money to double, right? So maybe you have $1,000 and you're wondering when it'll get to $2,000. And then there's a certain rate that you're given. Maybe it's growing at 5%, but you don't know how long it's going to take for it to double. Then now you've set up the question, how long will it take for 1,000 to double at 5% compounded continuously, which is not typically something the banks do for people. But perhaps this is a different situation, like bunnies or a substance that is growing or decaying. So you could throw in numbers. So how long does it take to double? You could just put a 10 and a 20, or you can put a P and a 2P. And so now you're trying to solve for T, which is again now a situation where you're trying to get that back. So regardless of whether you went P and 2P or 1,000 and 2,000 or 10 and 20, when you divide this part over to the other side, you're going to get 2, and then e to the 0.05t. And now, because you're trying to figure out what t is, you would take ln of both sides. And ln, because you have an e and the base e, is going to cancel that out nicely. So then now I could solve that and I could say the time is going to be whatever ln 2 is divided by 0.05. So this is a nice sort of general structure to refer to. So we'll see a few examples here. So this example, you have two populations given. In 2003, it was 16,400. In 2013 of the city, it was now 2,200, and we're assuming exponential growth. So we're assuming that we have this sort of situation with an initial population and then e to the kt. Find the function that models this population growth. So you have initial and resulting after t years. So you might want to think how many years have gone by from 2003 to 2013. So if you have 10 years, you started at 16,400, you're resulting in 2,200, and you've gone for 10 years. Right? So you've basically filled in everything you know, and now you're solving it. So just like we solved before, we'll take that, divide it, and we're trying to figure out what that constant is. So we're going to take ln of this, ln of that. So we have 10k equals ln of this number. And I'm not using a calculator, but basically, eventually your k will be the ln of this number divided by 10. So that's going to be approximately a certain value, and that's going to give you now the equation that you can use in general, starting with the 2003 population, for instance, and then you put your decimal, and then you say this represents the population growth for a number of years after 2003, for instance. That would be your formula. So then, if they ask you to predict 2018, you could think of, well, how many years is that from 2003? And you plug it into the formula, and then you'd be able to calculate it pretty quickly. Another example would be if you had like half-life or double life. So if a population of bacteria is doubling every 5 hours, so after t hours, what's going to happen? So we could start with this situation again. And again, like I haven't done this question, but I'm just starting with, okay, it's a generally this sort of situation. If I start with a 1 and it's going to become a 2, it's going to double. So I know that based on the fact that it's going to double. I also know that it's an E because it's natural growth. And I also know that it is going to double in 5 hours. So K times 5. And I don't know the K rate yet, but I can figure that out from this by solving it. And then I have a general equation to apply based on T hours, if that makes sense. So yeah, so 2 to 1, ln 2, ln of e to the 5k. I've just taken ln of both sides. That's going to give me just the 5k. And so when I divide it, so k is my ln 2 over 5. Ln 2 over 5. It's not going to be a very nice number. It's going to be about 0.139. In a life example like this, they want it to a certain number of decimal places. So you would keep it as initial times e to the 0.139 t for t hours. And that gives the general formula. And then that way you could figure out like 10 hours, or 10 hours would be easy, but like 8 hours or 23 hours. That's kind of what they're looking at again. And again, all of these, you're going to start seeing the same sort of thing. Like start with this, plug in what you know. If it just says doubles and you don't know initial value, just call it something 10 or 1 and then becoming a 2. And your goal is really just to find that k value first. So just don't be afraid of putting in some numbers for initial and resulting if it's just like a relationship or a ratio. Yeah, so same sort of types of questions. I can leave these sort of up for you. Again, this one's a decay because they're decreasing by 2%. So your k value will have to be a negative 0.02 t, e, and then Currently, there are 8,000 wolves. How long will it take until you have only 500 wolves? And so that's your equation that you're solving, again, in the same ways as before.